Imagine a place on Earth where the very air you breathe tastes like sulfur and rusty pennies, a landscape so hostile that the ground itself is permanently frozen to a depth of nearly 1,000 meters. This is not a scene from a post-apocalyptic fiction, nor is it a settlement on a distant moon, but rather the daily reality of the Taimyr Peninsula in the far north of Siberia. Here, 300 kilometers north of the Arctic Circle, lies the industrial fortress of Norilsk Nickel, a sprawling metallurgical complex that defies every law of logistical common sense and human endurance. It is a city built on permafrost, isolated from the rest of the world by a frozen ocean and a vast, roadless tundra, existing solely to tear valuable metal from the grip of the ice. The engineering required to keep this facility running is not merely about mining and smelting. It is a constant, violent war against physics, where temperatures drop to 60 degrees below 0 Celsius, snapping steel like glass, while inside the cavernous smelters, furnaces roar at thousands of degrees. To understand the scale of this operation, you must first strip away your conception of a standard factory. Most industrial plants are connected to the world by highways, rail networks, and power grids, allowing for the easy flow of parts and labor. Norilsk has none of this connectivity. It is an island of concrete and steel in a sea of snow, reachable only by air or by the treacherous northern sea route, which requires nuclear-powered icebreakers to smash a path through 2 meters of solid pack ice just to deliver supplies. The central conflict here is stark and terrifying. How do you maintain the precise high-temperature fluid dynamics required to smelt nickel and copper when the ambient environment is actively trying to freeze your machinery, your lubricants, and even the breath in your lungs? The stakes are absolute, for if the main power plant fails or the heating infrastructure collapses, the entire city would freeze solid within days, turning the complex into a tomb of ice and silence. The sheer audacity of building the Nadezhda metallurgical plant, the crown jewel of the Norilsk complex, is difficult to overstate. Constructed in the late 1970s, its name translates to hope, a cruel irony given the desolate landscape that surrounds it. The engineers who designed this leviathan had to solve the problem of permafrost, a layer of soil that remains frozen year-round. If you simply build a heavy factory on top of it, the heat from the building will melt the ice in the soil, turning the ground into a slurry of mud and causing the structure to buckle and collapse under its own weight. To combat this, every major structure in Norilsk, from the apartment blocks to the massive smelter halls, is elevated on reinforced concrete piles driven deep into the bedrock, creating a ventilated crawl space between the frozen ground and the warm floor of the factory. It is a city on stilts, tiptoeing over a sleeping frozen giant that could swallow it whole if it ever woke up. This is a world of sensory overload and brutal contrasts, where the darkness of the polar night stretches for 45 days and the sun simply refuses to rise. Under the artificial orange glow of sodium streetlights, the snow appears almost black, dusted with the particulate fallout of heavy industry. The wind does not just blow, it scours, stripping paint from metal and warmth from flesh in seconds. Yet, inside the plant, the atmosphere is tropical, heavy with the heat of molten slag and the hum of colossal electric motors. It is a testament to the stubbornness of industrial ambition, a place where humanity has carved a foothold through sheer force of will and millions of tons of concrete. If detailed technical breakdowns of heavy industrial engineering and extreme manufacturing interest you, subscribe. I have got more of these coming. Now, let us descend into the belly of the beast, specifically the flash smelting furnace operations at the Nadezhda plant, which represents the technical heart of this freezing empire. The process begins with the raw ore, which has been pulverized into a fine powder known as concentrate. This concentrate is rich in nickel, copper, and precious platinum group metals, but it is also laced with sulfur and iron, elements that must be purged with extreme prejudice. In a conventional smelter, you might use a reverberatory furnace, essentially a giant oven where fuel is burned above the ore to melt it. But Norilsk is too remote to rely entirely on imported fuel for such a massive volume of material. Instead, the engineers utilize the sulfur already present in the ore as the fuel source itself. This is the brilliance of flash smelting. It turns the rock's own chemical composition into the energy source that destroys it. The concentrate is dried until it contains less than 1% moisture, a critical step because any water entering the furnace could flash into steam and cause a catastrophic explosion. Imagine throwing a cup of water into a deep fryer, but scale that explosion up to the size of a 5-story building and you begin to understand the danger. Once dried, the fine gray powder is blasted into the reaction shaft of the furnace through a specially designed concentrate burner. Here, it meets a stream of oxygen-enriched air, heated to hundreds of degrees. The mixture ignites instantly. It is not unlike blowing a mouthful of flour into a candle flame to create a fireball, except here, the flour is heavy metal dust, and the candle is a continuous injection of pure oxygen. The sulfur in the ore reacts with the oxygen, burning with a ferocious intensity that drives the temperature inside the shaft to over 1,300 degrees Celsius. The particles of metal melt in midair, raining down into the settler hearth below, like a storm of liquid fire. In the hearth, gravity takes over. The heavier mat, containing the valuable nickel and copper, sinks to the bottom, while the lighter slag, composed mostly of iron and silica, floats on top. This separation is purely physical, reliant on density differences, much like oil floating on water, but the fluids involved are white-hot and viscous. The engineering challenge here is maintaining the refractory lining of the furnace. The bricks lining the vessel are subjected to thermal shock and chemical attack from the corrosive slag. To prevent the furnace from eating itself, the walls are cooled by hundreds of copper cooling elements, or staves, through which water circulates at high velocity. If a cooling pipe were to burst, water would hit the molten bath, expanding 1,600 times in volume instantly, turning the furnace into a bomb. The control room operators watch this process on screens, monitoring the thickness of the slag layer and the temperature of the melt with obsessive precision. They are balancing a thermal equation that must never tip. If the furnace runs too cold, the slag becomes sticky and viscous, refusing to flow out of the tap holes, potentially freezing the entire bath solid, a disaster that would require weeks of jackhammering to fix. If it runs too hot, the molten liquid becomes thin and aggressive, eroding the protective brickwork and risking a breakout, where liquid metal burns through the steel shell of the furnace and spills onto the factory floor. It is a high-wire act performed with hundreds of tons of molten rock. Stepping away from the furnace for a moment, the sensation on the smelter floor is overwhelming. The air is hot and dry, vibrating with a low-frequency rumble that you feel in your chest more than you hear with your ears. It is the sound of massive intake fans, the roar of the oxygen plant next door, and the rhythmic thumping of overhead cranes carrying ladles the size of small houses. The smell is distinctive, a metallic tang mixed with the acrid bite of sulfur dioxide, a scent that sticks to your clothes and hair long after you leave. In the shadows between the massive ductwork, dust dances in the beams of light, settling on every surface in a fine, dark layer. It is a place of shadows and blinding light where the sheer scale of the machinery makes a human being feel insignificant, a tiny biological cog in a geological machine. Returning to the technical process, we encounter a classic engineering trade-off, a nested loop of problem solving. We have successfully melted the ore using its own sulfur, but that sulfur has now been converted into sulfur dioxide gas, a potent pollutant that causes acid rain. In the early days of Norilsk, this gas was simply vented into the atmosphere, creating a dead zone around the city where no trees could grow. The forest surrounding the plant is a ghostly graveyard of bleached, dead trunks known as the Black Taiga. Today, modern environmental standards and international pressure force the capture of this gas. The exhaust from the flash furnace is channeled into massive waste heat boilers, which recover the thermal energy to generate steam for electricity. A clever reclamation of energy in this fuel-starved region. However, the gas must then be cleaned of dust in electrostatic precipitators. These are massive chambers filled with high-voltage electrodes. As the dirty gas flows through, the dust particles are given an electric charge and attracted to collection plates, snapping out of the air like iron filings to a magnet. The gas, now largely dust-free but still rich in sulfur dioxide, is sent to the acid plant or the elemental sulfur production unit. This is where the metallurgy turns into chemical engineering. The gas is passed over vanadium pentoxide catalysts, converting it into sulfuric acid, or chemically reducing it back to solid elemental sulfur, a yellow powder that is far easier to store and transport. But this solution creates a new logistical nightmare. The plant produces millions of tons of sulfur products that must be shipped out or stored, adding to the immense burden on the transport infrastructure. Every solution in this facility spawns a new, heavy problem to carry. Once the matte, the mixture of nickel and copper sulfides, is tapped from the flash furnace, it is still far from pure. It is transferred into Pierce-Smith converters, which look like massive horizontal cylinders lying on their sides. These vessels, easily 10 meters long and 4 meters in diameter, are mounted on trunnions that allow them to rotate. The converter is charged with the molten matte, and silica flux is added. Then a row of tuyères, pipes entering the side of the cylinder, blasts air into the liquid bath. This is a violent, chaotic process. The oxygen reacts with the remaining iron sulfide, oxidizing the iron, which then combines with the silica to form more slag. The converter spits and roars, flames shooting from its mouth as the impurities burn off. The crane operators overhead must be incredibly skilled, maneuvering ladles of molten metal with delicate precision while looking down into a crater of erupting sparks. The separation of the nickel from the copper is the next great hurdle. The result of the converting process is a high-grade matte that is essentially a mix of nickel, copper, and sulfur. To separate them, the matte is cooled slowly in insulated molds. This slow cooling is crucial because it allows the distinct metallic crystals to grow large. It is like growing rock candy, but instead of sugar, we are growing grains of copper sulfide and nickel sulfide. Once solid, the massive ingots are crushed and ground into a fine powder in ball mills, rotating steel drums filled with heavy steel balls that pulverize the rock. The powder is then subjected to froth flotation, a process that sounds almost delicate but operates on a massive industrial scale. In the flotation cells, the powdered matte is mixed with water and specific chemical reagents. Air is bubbled up from the bottom. The chemicals make the copper sulfide particles water repellent, so they attach themselves to the rising air bubbles, floating to the surface as a metallic froth that looks like shimmering dark gray soap suds. The nickel sulfide, however, remains wet and sinks to the bottom. It is a gravity-defying trick of surface chemistry that allows engineers to separate two metals that are chemically very similar. Imagine trying to separate salt from sugar after they have been mixed together, and you have an idea of the difficulty. The copper concentrate goes one way, to the copper plant, and the nickel concentrate goes another, to the fluid bed roasters and electric furnaces for final refining. Let us pause here and just breathe. The sheer density of operations in the hydrometallurgical wing is suffocating. There is no roar of fire here, just the wet, rhythmic churning of agitators and the hiss of steam pipes. The air is humid and smells of reagents, a sharp chemical odor that stings the nose. Rows of tanks stretch into the distance, filled with murky liquids where silent chemical battles are being fought. Outside the frosted windows, the wind might be howling across the tundra, but in here, It is a steady, controlled environment of pipes, valves, and gauges. It is the quiet, unglamorous side of metallurgy, far removed from the dramatic fireworks of the smelter, yet absolutely vital to the final product. The final stage for the nickel involves electrolytic refining. The impure nickel anodes are lowered into tanks filled with an electrolyte solution. Interleaved with them are thin sheets of pure nickel, the cathodes. When a massive electrical current is passed through the tank, the nickel atoms on the anode dissolve into the solution, swim across the gap, and deposit themselves onto the cathode. It is atom-by-atom reconstruction. The impurities, including the immensely valuable platinum and palladium, do not plate out. Instead, they fall to the bottom of the tank as anode slime. This unappealingly named sludge is actually one of the most valuable substances on Earth, containing the precious metals that power the world's catalytic converters and hydrogen fuel cells. Recovering this slime requires a security clearance higher than that of the gold reserves, as a single bucket of it could be worth a fortune. Knowing what you now know about its real-world production bottlenecks and extreme hazards, do you think the massive capital investment in this facility was worth it? Share your thoughts below. Now we must turn our gaze to the operational reality of this place, the friction between the theoretical blueprints and the grinding, dirty truth of the Arctic. The Norilsk complex does not exist in a vacuum. It is tethered to the world by the Yenisei River and the port of Dudinka. Dudinka is the lifeline. Every nut, bolt, heavy machine part, and liter of diesel must come in through this port, and every ton of finished metal must go out. But for half the year, the river is frozen solid. The port operations here are unique in the world because the river floods violently every spring during the thaw, submerging the lower docks under water and ice. As a result, the port cranes are mounted on rail tracks that allow them to retreat to higher ground before the floodwaters hit. It is a logistical dance with nature where the entire port infrastructure must migrate seasonally to avoid being destroyed. The ships that service this port are not ordinary freighters. They are the definition of heavy metal, reinforced Class Arc 7 container ships capable of breaking their own path through the ice. Picture a vessel the size of a skyscraper laid on its side, its bow shaped like a giant spoon. Instead of cutting through the ice, the ship rides up onto the ice sheet and uses its immense weight to crush it from above. The sound of this is terrifying. A screeching, groaning cacophony of steel against frozen water that reverberates through the hull. These ships carry the nickel and palladium to Rotterdam and Murmansk, navigating the northern sea route in perpetual twilight during the winter months. If a ship were to lose power here, there is no Coast Guard nearby to save it. It would drift into the pack ice and be crushed. The machinery inside the plant suffers just as much as the ships. The extreme temperature differentials between the outside air and the internal process heat wreak havoc on the metal structures. Steel becomes brittle in the cold, leading to cracks in crane girders and support columns. Lubricants turn into waxy sludge at -50 degrees, requiring heaters on every gearbox and hydraulic reservoir. A simple maintenance task, like changing a conveyor belt roller, becomes a life-threatening ordeal. A worker cannot expose bare skin for more than a minute without risking frostbite. Wrenching on cold steel requires thick gloves, reducing dexterity and making every movement clumsy and exhausting. The fatigue is not just physical, it is mental. The constant darkness of the polar winter messes with circadian rhythms, leading to sleep disorders and depression, a phenomenon known as polar hysteria. Then there is the issue of the permafrost itself. As the global climate warms, the frozen ground upon which Norilsk is built is beginning to soften. This is the nightmare scenario for the structural engineers. Concrete piles that have held firm for 40 years are starting to shift. Foundations are cracking. In 2020, a massive fuel storage tank collapsed because the piles supporting it sank into the thawing ground, spilling 20,000 tons of diesel fuel into the local river system. It was one of the worst environmental disasters in Arctic history, a brutal reminder that the engineering solutions of the Soviet era were designed for a climate that no longer exists. The plant is now fighting a two-front war, one against the coal to keep the processes running, and one against the heat to keep the ground frozen. The scale of the equipment used to move the ore from the mines to the processing plant is equally gargantuan. We are talking about underground dump trucks that are essentially low-profile, articulated beasts designed to navigate tunnels hundreds of meters below the surface. The mines, such as the Oktyabrski and Tymersky mines, extend over a kilometer deep. At those depths, the rock is under immense pressure. The rock mechanics engineers must constantly monitor for rock bursts, which are explosive failures of the mine walls caused by the stress of the earth trying to close the hole humanity has dug. The elevators that lower the miners drop at speeds that make your ears pop, plummeting into the hot, humid depths where the geothermal gradient raises the temperature to 30 degrees Celsius. The miners commute from the freezing surface to the sweltering deep every shift, a thermal shock that taxes the cardiovascular system. The sheer volume of material moved is staggering. The complex processes millions of tons of ore annually. To feed the hungry maw of the flash furnace, a ceaseless convoy of trains and conveyors must operate 24 hours a day. The railway system of Norilsk is an isolated network, unconnected to the main Russian rail grid. It exists solely to shuttle ore, coal, and workers. The locomotives are modified to handle the snowdrifts, equipped with massive plows. Yet, during a black blizzard, a storm where wind speeds exceed 40 meters per second and visibility drops to zero, even these trains can be buried. In such weather, the plant essentially goes into lockdown. Convoys of buses, linked together by heavy chains so none get lost in the whiteout, transport the shift workers. It is a scene reminiscent of an Arctic expedition, yet it is just the Tuesday morning commute in Norilsk. Let us take a moment to absorb the sensory reality of the waste dumps. Outside the city, vast tailings ponds stretch for kilometers, holding the crushed rock residue from the concentrators. In the winter, these are frozen white plains, indistinguishable from the tundra until you see the unnatural flatness. In the summer, they are dusty gray wastelands. The wind whips up the fine silica dust, creating choking clouds that coat the city. The silence out here is profound, broken only by the distant hum of the plant and the cry of an occasional gull that has strayed too far inland. It is a landscape of industrial aftermath, a necessary scar for the metals we crave. Despite the grim atmosphere and the brutal conditions, the legacy of Norilsk nickel is undeniable. It is a paradox of the modern world. We demand a green future, powered by electric vehicles and hydrogen energy. Yet, that green future is built on the back of metals like nickel, copper, and palladium. Nickel for the high-capacity batteries in our cars, copper for the windings in wind turbine generators, palladium for the catalytic converters that clean our exhaust and the fuel cells of the future. Norilsk is the largest producer of palladium in the world and a top-tier producer of high-grade nickel. The clean air of European cities and the electric revolution of California are directly tethered to the dirty, freezing reality of this Siberian outpost. The engineers who keep this place running are masters of adaptation. They have developed unique stainless steel alloys to resist the specific corrosion of the local ores. They have invented methods of construction that allow buildings to float on shifting ice. They operate the most northern major industrial facility on the planet, proving that human ingenuity can function in environments that are biologically incompatible with our survival. It is a testament to the brute force of industrialization, a reminder that civilization's comforts are forged in places of extreme discomfort. The conflict between the ice and the fire is never truly won. It is only managed day by day, shift by shift. The flash smelting furnace will continue to roar, consuming the powdered rock and spitting out liquid metal, as long as the engineers can keep the oxygen flowing and the cooling water from freezing. The icebreakers will continue to batter the frozen Yenisei, keeping the artery to the world open. And the people of Norilsk will continue to endure the polar night, living in the shadow of the smoking stacks, knowing that their labor powers the modern world. It is a place of heavy metal in every sense of the word, heavy machinery, heavy elements, and a heavy toll on the land and the people. But as you watch the latest electric car glide silently down a clean city street, remember the screaming wind, the black snow, and the roar of the flash furnace in the high Arctic that made it possible. The distance between the consumer and the source is vast, but the connection is absolute. We live in a world built on the periodic table, and Norilsk is where we go to rip those elements from the frozen earth. If you found this analysis useful, a like helps more people discover these deep dives. Thanks for watching.